Very good. Okay, last time we had left off talking about the reaction progress variable and the lower and upper bounds. Okay, so when you have a reaction, you're varying the progress variable between the leftmost and the rightmost values. And we've seen that depending on the reaction and depending on the initial composition, okay, you can have any sort of lower and upper bound for the progress variable. In this particular case, if you remember, for this reaction here, right, we found essentially that the progress variable, maybe it's better if I write with a bolder thing. I don't know. We'll see. So we found the two values here of which was N0C, which is the initial number of moles of C divided by gamma, and then minus the initial number of moles of plus the initial number of moles of B divided by beta. Now, why C and B? Because if you remember, C was the limiting product. So if you shift the whole thing to the left, this is the first one to be depleted. So C is the limiting product. Okay, and same thing with B is the limiting reactant. So you shift everything on the right, and you have that in this particular case. Okay, you have that B is the limiting reactant. So when it's so shifted to the right, it's the first one to be depleted. Okay. Now, is this always true? Obviously not. Suppose that I change my initial composition from here, okay, to, I don't know, somewhere like here where I have a lot more of B, okay, of species B. So what's going to happen here now, because I've changed my initial composition, as I proceed and I shift this reaction from left to fully to the right, I'll have to go parallel to that line here, but you see that now the first species to be depleted, the first reactant to be depleted is A. So in this case, A would be the limiting reactant. So it's all dependent on the stoichiometry, alpha, beta, gamma, delta, and the initial composition N0 of each species, okay? In general, if you have the usual, reaction, which we write in these terms, okay, the reaction progress variable will essentially vary between a lower bound, which is essentially 0 minus N0I, okay, divided by the stoichiometry, okay? So this would be my psi L, where species I is my clearly limiting reactant, okay? Sorry, product. I always get mixed up. On the left is clearly product because we're shifting from the right to the left, so fully to the left, so you have a product that is being depleted. So I is the limiting product. And you have something like, well, let's call it J, okay, in this case, or the limiting reactant. So that would be my value side right, okay, the upper bound. And J is the limiting reactant. Well, I mean, I've spent too much time on this. It's a pretty straightforward concept. I can give you, for example, some exercises, okay? So if you, well, I won't spend too much time on these, but if you have a reaction of the sort with between hydrogen and oxygen, okay? I'm giving you the stoichiometry clearly. Now I'm going to have to give you my initial composition. So for hydrogen would be, for example, 2. Oxygen, for example, 2 moles. And you may have also 1 mole, for example, of H2O. Okay? So you follow exactly the procedure as before. So for psi L, you essentially think of the reaction completely shifted to the left. Okay, so obviously you have just one product, so clearly the limiting product is clearly just water. So if I go, okay, if I apply this or this notation here, clearly I would have that NH2O minus N minus initial divided by, clearly now it's 1 minus 0, so simply 1. Now I depleted, so it's 0 minus the initial, which is 1 mole in this case, divided by 1, so that would be minus 1. So that's my leftmost reactant. Okay. Now, if I do for the right, I would have to choose whether H2 or O2 is depleted first. Okay. So I will essentially express the number of moles of H2 as a function of the number of moles of O2. So let me just skip a few steps here, but it's easy to see that it would be something like this. So initial number of moles of H2 is equal to the initial number of moles of H2 plus 2 NO2 minus NO2 initial. So it's essentially 2 plus 2 NO2 minus 2. Okay, I'm just using essentially the definition of progress variable and the fact that the ratio of NH2 minus NH20 divided by the stoichiometry is equal to the same thing for the oxygen. And all you have to do now is draw the usual graph where essentially you have number of moles of H2 here, number of moles of O2 here. They're both starting at 2 moles. Okay, but if you draw this this line, you'll soon realize that the limiting reactant is hydrogen. Okay, it's the first one to be depleted. Okay, and therefore what we have to do is simply write down the ratio for hydrogen. Okay, we deplete it first, so we impose that it's 0, okay? Minus 2 initial moles divided by minus 1, so that would be 2. And that's our psi R. Let's see if Someone is asking something. Can you see the screen?
Yes, Prof.
Okay, so why? Okay. Someone cannot see it? Okay. Let's see if I have. So in this case, psi varies between -1 and +2. Okay. Let's see if I have some exercises for you. You can obviously now have fun. I won't do it. I won't waste too much time to see this in the 3D space. Okay. Where you have H2O, O2, and H2. Okay. And you can see, for example, that you will have a certain initial condition, and then basically your reaction will go from this plane to this plane here, okay? And this will be your psi right, and this will be your psi left. And you can really reproduce visually, okay, this sort of graphical interpretation of the reaction, okay? There are, for example, you can try doing the same thing now. You can do it by yourselves when you have time. Take the same reaction, okay, but change now the initial composition. So, for example, you may have. So what you're doing is actually shifting this point here, but clearly the reaction will always be parallel, okay, because remember, a reaction is a direction, remember, in this phase space. So you can start from 3 moles, okay, of H2, 2 moles of O2, and whatever, 3 moles of H2O. So you see now that you can start from any number of moles, clearly. You are now implicitly adding an elemental composition, so an overall number of atoms that you will have to conserve. Okay, and you can see that if you carry out the same procedure, now the limits will be -3 and 3. So you can verify that. Okay. Okay, so that's that. Now we'll shift to a more interesting part, which is essentially what we said before. Okay, you may have heard, you may have realized now that it's a very slow process towards really trying to figure out how, for a chemical system, we can write down, remember, the Gibbs energy function, okay? And in fact, if we have this representation in terms of one or more reactions, okay, that are actually little composition changing machines, okay, that can actually perturb your system through these permeable walls, so to speak, then I'll be able to write it down as a function of, say, multiple progress variables, or just one if I have one reaction, okay? And if I know how to write down this function, then I hope you agree with me that if I now determine the minimum point, okay, the global minimum of this function, I will have found the equilibrium point, right? Now, let's draw a line here to remind ourselves that we've changed subject, okay? Now, let me remind you this fact a little bit better. So remember that our condition of equilibrium for a constant temperature and pressure system was this, right? A minimum of Gibbs energy, okay? And well, the differential of the Gibbs energy at constant temperature and pressure, you can really write down as the summation, okay, of our chemical potentials, okay, of each species times dNi, okay? But remember that if I have a generic reaction, okay, so consider one reaction, okay, we've been writing over and over again that the composition is equal to the initial composition plus the difference in stoichiometric coefficients related obviously to species I times the reaction progress variable. So I can really express any differential change in the composition of species I as essentially this, right? Times d psi, okay? So you see that now if I go back here, I can substitute, okay, for dNi, this expression here. And in fact, the d psi goes out because it doesn't depend on I, and that would be essentially equal to 0. That's my condition of equilibrium. In fact, I can even express this differently in saying that the slope must be 0, right? So if I divide by d psi, the slope is equal to this guy here, this expression here. Okay, this must be equal to 0. Okay, so you're beginning to think now to think of G as this graph, okay, of G as a function of psi, and this is clearly the minimum point, and this is the expression. Okay. Now, well, we've seen it already. We can repeat it clearly if we write, for example, if we rewrite this, okay. Okay, as this expression here. Remember that if we perturb the system with respect to the equilibrium point, okay, remember? So if we change the composition forcibly, okay, if we force it maybe by driving this reaction a little bit more to the right or to the left with respect to the equilibrium, and then we let it go spontaneously, you will remember that the system will respond spontaneously so as to decrease the Gibbs energy, remember? So clearly, if we move or we shift the reaction towards from left to right, so we increase psi, okay? And so we essentially move the reaction from left to right, okay? We shift it a little bit to the right because now the system will respond spontaneously to restore dg, which is always decreasing, so dg is less than 0, then clearly you have that the slope of this guy here, dg by d psi, is negative, okay? And the same thing if you go from right to left. Can you hear? What is this? Wait. I don't know whether you guys, you come this late or you get kicked out. Anyway, so if you decrease the progress variable, dg must always be negative, and so the slope now is obviously positive. What does this mean? It means that if we are to represent, this function on a graph, okay, between, so this is psi, between the leftmost and the rightmost values of psi, okay, we have a value here, which is my equilibrium point, right? And essentially, on the left of this, we'll have a negative slope, okay, clearly. And on the right, we will have a positive slope, okay? Something like this. So this is essentially my function g of psi, okay? So when we perturb from the equilibrium point, this will be the direction of which spontaneously the system will move, because it will spontaneously go towards a decrease, okay? So dg goes to 0, and obviously in this case here, dg is also less than 0, okay? And this translates into slopes being negative and positive, okay? So essentially, there is a minimum, okay? So let's go back to our initial sort of problem. Okay, but how do we express this? How do we find it, okay, explicitly? Well, we have all that it takes, because if you remember, G is extensive, okay? G, like every other chemical potential, is really an extensive quantity, okay? So it's homogeneous, remember, first order. So generally speaking, G you can express as a function, well, of T and P, which, well, are my two intensive quantities or intensive variables, but really it all is also a function of all the composition, so all the number of moles, and the number of moles are extensive, okay? So we'll have N1, etc., N2, and N like this, okay? And these are clearly extensive. Now, remember that for any first order homogeneous function, you could multiply the extensive quantities, so let's do it here, by a factor. So if we multiply each of those by lambda, okay, you could rewrite this as lambda to the 1, remember, so that's why it's first order homogeneous, okay? So you could just take it out, okay? And it means that it's additive over constituent subsystems. That's one property. And through this property, we proved Euler's theorem, okay? If you remember. Euler's theorem, which is valid for these kinds of homogeneous first order functions, says that G, okay, can really be expressed. So this means that you have a series of number of moles here, okay? It can be expressed as the summation, remember, of quantities which are the partial molar quantities, dg by dni, calculated at constant T, constant pressure, okay, times the number of moles. Now, And I'll repeat it here in short. So G is equal to okay, I will put it in a box because this is really one of the most important relations, okay, that we will use. Okay, it's really the basic relation, okay, that we'll be using. So this is not a differential, okay, relation. Okay, there's no dg. This is the actual function, which because it is extensive, so because it is homogeneous first order, can be written as the summation of these derivatives, okay? And if you remember what these derivatives were, they were the chemical potentials. Okay? So let me stress this once more. I mean, we are applying, we've constructed, you know, in some sense, a theory of thermodynamics, and for all of those extensive variables, really, we found a way of actually writing them down explicitly using Euler's theorem. Okay? So if our initial problem is, okay, to actually find an explicit function for G that we can eventually minimize, then look, the problem now is shifted towards finding an expression for the chemical potential. Okay, I'll write it here. We need an expression for the chemical potentials of each species, mu y. Okay. I will go back to what you may have noticed that I've used the term partial molar Gibbs energy, okay, for the chemical potential. Again, that's another very important concept. I'm going to go back to it a little bit later on, but it is one of the important concepts to keep in mind. So the chemical potential, I'll write it here. Okay. And the fact that I'm adding the word partial to molar, it means that it's really a different concept, okay, than just a molar Gibbs energy, okay? It's really a completely different concept. And I will anticipate it now in a few words, but essentially the difference here is that we're creating mixtures, okay? We're dealing with a multi-component system, okay? You may have noticed that our chemical systems is composed of several species. The species that appear in the reaction is hydrogen, oxygen, and water. Now you have to mix them, right? They're homogeneously mixed, okay? And we really need a way to understand how the Gibbs energy, and in fact all other extensive quantities, will change, okay, when you add a single mole, okay, of one of the many species that composes a system. So these two concepts are different. The partial molar concept and the molar concept are different because in the molar concept, what you're doing, you're measuring, for example, the Gibbs energy per unit mole of the mixture, okay? But if you take a mole of the mixture, you will have essentially all of the species, okay, in their sort of right proportion, okay? On the other hand, the partial molar quantities say something completely different, okay? What happens to the mixture if I add 1 mole of a pure species, for example, hydrogen, okay, to the whole mixture. And this will turn out to be a crucial concept. But we'll get back to it. Now, let's go back to here, okay? We want to write down G, so through Euler's theorem, we realize that we need an expression now for the chemical potentials. How do we write down an explicit form of the chemical potentials in terms of, say, the state variables, like pressure, like temperature, like volume? Well, we have to specialize our system, okay? What do I mean by that? Well, we have to take our thermodynamic system, composed of multi-components, and we have to specialize it. We have to give it essentially an equation of state, okay? We have to say, okay, this is, for example, a perfect gas, okay? So by specializing, I mean actually either through experimental relationships, we have to know how, for example, temperature, pressure, and volume are related, okay? And not all systems are related in the same way. In fact, as you know, for what we call as an ideal gas, okay, the intermolecular forces become negligible, okay? So that means essentially this. It's a very good, very strong simplification. It's a good model in the sense that it models almost all of the gases that you have essentially at atmospheric pressure and at temperatures that are essentially not too cold, okay? And so at low temperatures, or at low pressures, so for example, atmospheric pressure for me is low because clearly the pressures that you have in engines, like in rocket engines, we're talking about 300 bar. That's not low, okay? So the higher the pressure, the more these molecules will stay together, will be driven together, and that's when the intermolecular forces will take over. But if you are at a reasonably low pressure, then these intermolecular forces, especially if the temperature is high, okay, and the kinetic energy, the average kinetic energy is essentially much greater than these intermolecular forces, well, we can safely disregard, okay, the effect of intermolecular forces, okay? There is also, and this is typically a perfect gas is typically such when the temperature is higher than the so-called critical temperature and the pressure is lower than the critical pressure, okay? And the critical, essentially, pressure and temperature is a particular point, okay, of a state diagram where essentially we cease to have the transition between liquid and gas, okay? So we're much hotter than that and at pressures that are quite low. So I'll give you an example. For example, for oxygen, it's about 50 bar. So the critical pressure, so at 1 bar, at atmospheric pressure, we're much lower than that, okay? And the temperatures are, typically the critical temperatures are cryogenic, so very, very low, like minus 150 degrees Kelvin, for example. So clearly at room temperature, we're far beyond that, and therefore we can say that the oxygen behaves as a perfect gas, okay? Now, I'll go through this quite easily. So we need an equation of state, okay, that characterizes our gas, our perfect gas. Can you hear me? You can, right?
Sì, si sente.
Allora, in order to have an equation of state, I'll write it equation of state, okay? what's usually done is we put together three basic laws. Sorry. Three basic laws, which are really experimental laws. Well, Boyle's law, for example, is the first one, and will essentially tell us that volume is inversely proportional to pressure. Sorry about this. Should switch off the. So what this says essentially, so this is Boyle's law. So if we keep the temperature constant and for the same amount, so for the same number of moles, okay, N, okay, so for the same quantity of gas at a given temperature, okay, what this says is that pressure is inversely proportional to volume, as we know, okay? On the other hand, okay, another law says that, so K is a proportionality constant of some kind, and B will be 2, another proportionality constant. So Charles' law says that at a given pressure, for the same number of moles, so given its quantity of substance at the same pressure, the volume is proportional essentially to the temperature. Okay, so the higher the temperature, the higher the volume, if you want to keep the pressure constant. And this again is for the same quantity of gas. Okay, and then finally we have that the volume is also proportional to the quantity, okay, of substance, and this is known as Avogadro's law. Okay, so if you keep your temperature and pressure constant, okay, you don't change that, the volume is proportional to the number of molecules, okay, essentially. And this is quite remarkable because this is independent of the kind of molecule, okay? It's always the same, okay? And why is that? Well, because essentially when you're dealing with a perfect gas, okay, the average distance between molecules is so big, essentially, that you can treat molecules as particles of independently of whatever they are. Okay. So if I have the same number of molecules, okay, that will occupy the same volume at constant temperature and pressure, irrespective of what kind of molecule you have. Okay. Again, because the volume occupied by the molecules themselves is absolutely negligible. Okay. We put everything together, and we can write something like V over N is equal to a constant, which is equal to a universal constant valid for all gases, T divided by P. Okay, so a constant temperature and pressure, okay, V over N is constant, for example. Okay. So equal volumes of all gases, okay, at Tp constant, okay, essentially contain the same number of molecules. Okay, and this is our first form of our equation of state, which we all know, by the way. The universal constant is a product of Avogadro's number times the Boltzmann constant, and it's equal to this number here, so 8,315 joule per kilomole per Kelvin, okay? Avogadro's number is something like 6 times 10 to the 23. The units are per unit mole, so molecules per unit mole, okay? And Boltzmann constant, on the other hand, is 1.38 times 10 to the minus 23 joules per Kelvin, okay? Let me write down another basic relation that we'll need, which is that the mass is related to the number of moles, okay, through a molecular weight, okay? So this could be, for example, the molecular weight of the mixture, the average molecular weight, okay, depending on the composition, but it could also be for a pure substance. It could be just the molecular weight of that pure substance, okay? And remember that the molecular weight has units of gram per unit mole, okay? So if you multiply by the number of moles, you have grams. And so let's write down our equation of state in another form. So we multiply by P. So you have P times the volume, okay, is equal to the number of moles times your universal gas constant times T. I will use this script kind of form when I talk about the universal gas constant, which is the same for all species, but for all gases. But if you convert moles into mass, okay, you'll see that you have to divide by essentially the molecular weight. Okay, and so when you write it in the form of mass, you're not using the universal gas constant, but you're using this other R, which depends on the gas itself, okay? Because it's divided by the molecular weight, okay? And so from this, you have all the known, so let me write it. So R is essentially the gas constant, not the universal gas constant, okay? You can have all the known forms, okay? So for example, if we divide by the mass, okay? Well, here you have a volume per unit mass, which is the inverse of a density. So it's pressure divided by density. Or pressure times, well, the reciprocal of density is specific volume, okay? So specific volume is measured in meter cubed per kilogram, okay? And that's equal to R T. Therefore, you can also write down the most sort of the known form, which is rho RT, okay? I'm just revising here. The only thing that it's actually worth mentioning is the ways in which we deal with composition, okay? The relative quantity of each species within a mixture, okay? So a mixture is essentially composed of n species, so n1, n2, etc., or ns, for example, number of species. This is the number of moles of each species. So there's also a total number of moles, okay, which is nothing else but the sum, okay, of each species, okay? Now, suppose that I have a container, okay, where I have a certain mixture composed of Give me 1 second. Give me just 1 second. I'm sorry, but okay. So can you hear me?
Sì, sì. Sì.
Okay. So suppose that I have a container full of, containing a mixture, so different number of moles of each species, okay, at pressure P, okay. What you can think is, and this is a volume V, okay. You can think of the same volume. Okay, I'll try to draw it, but obviously it's difficult. Okay, filled only with, say, one species. Okay, so it's only occupied by this species. Clearly, the pressure that you'll have is not the same, and we call it the partial pressure, PI. Okay, so using the equation of state, okay, PIV is equal to NIRT. Okay. In fact, if you divide by an I, this we call the molar volume. Okay. VI. I'll just differentiate it from the specific volume by a little bar over bar. Okay. And it's in meter cubed per mole. Okay. But in any case, this is, okay, our equation of state, okay, where the volume V is occupied just by one species. Okay. So now I can compare, for example, the mixture. So the mixture, for the whole mixture, you have a total pressure P. V is equal to what? The total number of moles, which is clearly the sum, okay, of all my number of moles, okay, multiplying RT. So that's the mixture. So it's this situation here, okay? On the other hand, okay, if you only have I, so this situation here, as we said, we have partial pressure, V equals NIRT. Okay, so here we only have one species in the same volume. So if you divide one by the other, okay, essentially PI over P, all you get is essentially that you get the ratio of the number of moles of Ni divided by the total number of moles. Okay, so Ni divided by the total number of moles, and this, by definition, is what we call the molar fraction. Okay, mole fraction, and it's a number obviously between 0 and 1. Okay, and it is another way of actually addressing the composition clearly. Okay, of a mixture. Okay, each mixture will be present in the mixture. Sorry, each species will be present in the mixture with its own mole fraction. Okay. The partial pressures, therefore, in some sense, are defined as the mole fraction times the total pressure P. Okay. Okay. Note that if I sum all of the mole fractions, okay, for all species up to NS, okay, well, essentially I will have this situation here. I will have the sum of the total of the number of moles divided by the total number of moles, but that's by definition n total divided by n total, which is 1. So every time you sum on all the mole fractions, okay, they all sum up to 1. Okay, so each mole fraction essentially is a fraction, clearly. Collectively, they sum up to 1. And therefore, the sum of the partial pressures, by definition, is P times the sum of all the mole fraction, which is 1, and therefore the sum of all the partial pressures is actually P itself. Okay. What else? Well, there are, depending what you divide with, you have all sorts of definitions. For example, let's go back to our equation of state. Okay. You can divide by volume. And now what you have essentially, well, is what we call a molar concentration, okay? Which we call C. Okay, so this is the concentration in terms of moles. So it's essentially C will be the inverse, okay, of what we've defined before as the molar volume, and essentially is measured in moles per cubic meter. Okay. Again, if you sum on all the molar concentrations, okay, we call this the total concentration, and it's essentially the total number of moles divided by the volume, okay? So this is essentially the total number of moles per unit volume, okay? Or total concentration. Or molar concentration. Okay? Let's introduce the mass fractions. So PIV is equal to the number of moles now times RT, but the number of moles can be written as the mass of each species. So I'm writing the partial pressure version here. Divided by the molecular weight of the species I, so that's the number of moles, okay, times RT, okay? And again, R divided by the molecular weight is equal to the gas constant, referred to species I, okay? If we can further divide this by volume, okay? And we have the mass of I divided by the volume times RIT, which is equal to rho I, okay? Which is a mass concentration, okay? Of species I, okay? So obviously in kilogram per cubic meter. Let's see about this mass concentration of I. We said by definition is equal to the mass divided by the volume, okay? Well, you can multiply top and bottom by rho, and clearly now at the denominator you have the total mass, okay, of the system, which is essentially the summation of all the masses of all those constituents. And then you have rho mi. So here, essentially, you have rho, which multiplies this ratio here, mi over the total number of, the total mass, which is essentially the mass fraction. So essentially, it's a mass, in mass base, it's the same thing as what the mole fraction was for moles, okay? And therefore, we can write down, well, I'll write it down here, the relationship between mass fractions and mass concentrations, okay? Which is, in some sense, similar to the partial pressures and the mole fraction relationship that we saw earlier, okay? You can prove very easily that just like with mole fractions, the sum of all the mole fraction is equal to, the mass fraction is equal to 1, okay? And you can also relate mass and mole fractions, okay? Unfortunately, this is a sort of language that we have to learn, okay? Especially when you have mixtures. You have many ways in which you can characterize a mixture. They're all equivalent, clearly. So by definition, this would be the ratio of the mass of species I divided by the total mass, right? We can multiply now by the molecular weight of species I, okay? Actually, wait a minute. Let's do something different. Let's just implement the definition here. Simply number of moles, okay, times the molecular weight, okay? And here the same. So we have the summation of Ni times the molecular weight, okay? If you divide by the total number of moles, the numerator and denominator, like this, you have something of this sort. Okay? And clearly, this by definition is your mole fraction, okay? And in here you have something like the sum of the mole fractions times the molecular weight. We call this denominator, okay, because it's like a weighted average, okay, where the weights are the mole fraction of the molecular weights. This is the mixture average, okay, molar weight or molecular weight. And so the relationship between the mass fraction and the mole fraction is essentially this, okay? They are, they differ by this factor here, which is the ratio of the molecular weight to the mixture average molecular weight, okay? Another concept that you all are familiar with is the concept of specific heat capacities, okay? And that's the last concept I will introduce, okay? Let's see if I can make it brief. Let's recall how we write down the differential form of the fundamental equation. So this is the differential form of the internal energy, TdS minus TdV plus the sum of all the chemical potentials, okay? Now, this is clearly the part of du, okay, total du, which you essentially calculate a constant volume, okay, where dV is 0 and the composition is kept constant, okay? So clearly, this is T ds, okay, which to remind ourselves that we're keeping volume and number of moles constant, we can write this. And this is TdS is clearly what? It's heat exchanged, okay, at constant volume and number of moles, okay? So this term here is essentially the heat exchange at constant volume and when composition doesn't change, okay? The same thing can be done with enthalpy, okay? Because you still have a TdS here plus VdP plus your chemical potentials, okay? So this is the part of variation of enthalpy that you carry out at constant pressure. So this is 0 and constant composition, okay? And this is again a heat exchanged when you're keeping the pressure constant and you're not changing the composition. So essentially what you're doing is you have a system, you're not changing the composition of this system, you're giving heat to it. You can either give heat by keeping the volume constant, or you can give heat to the system by letting its volume change so that the pressure remains constant. In this latter case, the system will also expand and do work on the surroundings, okay? So the question is essentially, how much heat do I have to give the system in order to, for example, increase the temperature by the unit temperature or by 1 Kelvin? And this is a quantity that is measured through the specific heats, okay? So the easy way is you consider a pure substance, okay? And you consider the specific heat at constant pressure, for example, okay? So what you're doing is you're measuring this heat here, exchanged at constant pressure per unit temperature, okay? Actually, this should be a differential, okay? the way I'm writing, the reason I'm writing this, you know, it's not a perfect differential. At constant P and composition, we will have to divide here by the total number of moles, simply because we're interested in the amount of heat per unit mole, for example. But we could also have it in mass form, so per unit mass, okay? So it's the amount of heat needed to raise the temperature by the unit Kelvin, okay, for a unit quantity, which is, for example, 1 mole of quantity. Okay, this is clearly now, we can write it as 1 over n dH by dt. And if we incorporate this n here, we have the specific, in this case molar, okay, enthalpy by dt, okay? Still a constant P and N, okay? So this is essentially the variation of the specific enthalpy, okay, for the unit variation of temperature. But I mean, practically speaking, is how much heat we need to raise the temperature by 1 Kelvin for the unit quantity of substance to be raised the temperature by 1 Kelvin, okay? And the same identical thing you can do for a constant volume, okay? CV, okay, it's defined as, again, the unit mass, the heat exchange by unit mass and by temperature at constant volume and number of moles, okay? And again, we're using now not the enthalpy, but the internal energy. And so ultimately is the specific internal energy. So remember that the big letter, the capital letter, is the extensive quantity. If we divide by the unit mass or the unit volume, the unit mole, then we have lowercase, okay? And that's the specific quantity. Right. Generally speaking, looking at the intensive quantities, so the specific quantities, we could write this as du by dt at constant volume and number of moles by dt, so that would be CV. But in theory, you could also have du by dV, for example. Okay, at constant temperature and composition. Okay, same thing. For example, for enthalpy, you can have Cp, which is dH by dt. Okay, at constant pressure and moles, plus another contribution, which is dH by dP, okay, at constant temperature. No, sorry, this is temperature. Yeah, okay. This is temperature. I don't know why this doesn't work. dP. But as you know, whoa. Wow. Sorry. I don't know why it's so slow. Oh, I think I know, because I have to clear the, I will clear the, because everything is in memory now. So if I don't clear this, it's slower and slower. So that's dt and that's dP, okay? But as you know, these terms for a perfect gas are 0. Okay, if you may remember that essentially for a monatomic perfect gas, we have an expression for the extensive quantity internal energy as a function of just temperature. Okay, so it's 3 divided by 2 nRT. So you divide by number of moles, you have the specific quantity is essentially 3/2 RT. So you see that U is just a function of temperature. Okay, it's not a function of either volume, for example. And the same thing with enthalpy. H being H equal 1 plus PV, sorry, U plus PV. We know that U is a function of temperature and PV is simply nRT. So if we divide by the number of moles, we have UT plus RT. So you see that even H is only a function of temperature. So these two are essentially 0. Okay. The reason that you have well, it's not moving anymore. Let's see. Okay. So essentially, we can rewrite these two as this quantity here, which is CV as a function of temperature times dT, and dH as Cp as a function of temperature times dT. And these functions, Cp and Cv, generally speaking, increase with temperature. Okay. So for a monatomic, so this is, for example, Cp. For a monatomic molecule, so like, for example, atomic nitrogen, you have this increase essentially because as you increase the temperature, the capacity of the molecules to store energy at constant volume or constant pressure increases because they progressively activate translational. And then if it's a multi-atomic, so for example, a triatomic molecule such as CO2, okay, it will increase even further because it will activate also rotational degrees of freedom. Okay, so they can absorb essentially through these degrees of freedom more energy. Okay. And clearly we know that from here, from this relationship U plus RT, we know that dH by dt at constant pressure, which is Cp, okay, will be equal to du by dt plus R. So you see we have Cv plus R. So there is this difference between Cp and Cv simply because Cp is larger, having the capability of these systems to also do work towards the surroundings. So it needs more heat, okay, to increase its unit temperature. Okay, but these are all things that we know. Now let me just clear the canvas. I may want to probably save it first, but I don't know how to do this because there is no option saving it, so who cares? Let's clear the canvas. Yeah, if you write too much, then it's oh, I should have done export, but who cares? Okay. Oh, finally. Okay, good. So we've done this. Okay, now we have everything that is essentially needed to talk about chemical potentials. Because if you remember, I'll write it here, our goal was to find this function. And we said that G, okay, can be expressed like this, okay? And so essentially, we want an expression for the chemical potential. But now we have specialized our system to a perfect gas. And so we have a lot more tools, okay, to try and write down an expression for this quantity here, okay? Remember that this quantity here was defined as dG by dNi, okay? At constant pressure and temperature. And in fact, also all the other species except I, okay, are kept constant, okay? And this we had defined as a partial molar, okay, Gibbs energy. Now, let's talk about these partial molar quantities. And what they mean. So let's generalize the discussion, okay? Suppose we have an extensive property of some kind. So this is I call it property, okay? It could be a chemical potential of some kind, okay? We call it, it could be the Gibbs energy for all that matter. But let's call it generically A as a function of, for example, just like Gibbs energy, temperature and pressure, and then all the extensive number of moles, okay? So N1, N2, and Ns, okay? So this is extensive, okay? It's additive over constituent subsystems. It is also homogeneous first order function, and we can apply Euler's theorem to it, which is Euler's theorem, I'd like to remind you, is this, okay? So let's write it down, okay? Let's again remind ourselves that if we multiply by a factor, lambda, okay, the factor can be taken out with the power of 1, okay? And that essentially means that it's additive over constituent subsystems, okay? So it's extensive. That's the definition, okay, of extensive function or homogeneous first order function. And for this, we can also apply Euler's theorem, which says the following, okay? So I'm just repeating everything we know for the property, the extensive property A. Okay? So that's temperature, pressure, and everything else but I being kept constant, okay? And this is NS. Right. Now, by definition, okay, and this is a total definition, we define this quantity here, dA by dNi, so this derivative here, okay, is again calculated at constant temperature, pressure, and I divided by J, sorry, different from J, and we give it the name A subscript I, okay? This will be called the partial molar quantity referred to A. So if A is like the Gibbs energy, then it's going to be the partial molar Gibbs energy, okay? So let's put it under, okay, under a box just to say that this is a definition, okay? Now we'll see what this means, okay? Clearly, A will have a very easy expression if once we know all the partial molar quantities, as we said, because we can write it using the Euler's theorem, okay? So exactly like we did for the Gibbs energy, okay? So we haven't done anything else. Also, the partial molar quantity, because it's the ratio of an extensive quantity and another extensive quantity, well, this is an intensive quantity, okay? So AI will be homogeneous, zero order, okay? I hope we agree with that. Now, the difference here, as I was saying at the beginning of the lecture, is with what we're used to calling as intensive or molar quantity. So that's right here. This is intensive. Okay. Now, a specific or molar quantity would be something completely different. We're used to taking A, right, and writing down the specific or molar quantity with a lowercase letter a, okay? So we take essentially our quantity A and we divide it by, for example, the total number of moles, okay? So we take A per unit mole, okay, over N. Now, what's the difference here between a specific, or in this case, molar quantity and a partial molar quantity? So here you only have this molar quantity, but here you have this partial word, okay, in addition, okay? So what is the difference between the two? Well, the difference is in the fact that we're dealing with multi-species systems, okay? We're dealing with systems that are composed of several species, okay? So, the partial molar quantity, and I'm going to give you the definition now, well, is associated to component I. Okay, so let me just write it down. So the partial molar quantity AI, okay, of the ith component of a mixture, okay, is the variation of A okay, of the quantity A as a result, okay, of the addition of just 1 mole of only species I, okay? So you have a mixture, you add the unit mole of species I, and AI will be the variation of your property, extensive property A. Is the variation of A when 1 mole of only, okay, species I is added to the mixture. Okay? Let me add at P and T constant. So we're keeping the pressure constant, we're keeping the temperature constant, we're not touching all the other species, but we're adding to the system 1 mole of only pure substance, okay, I. It could be, for example, a mixture of hydrogen, oxygen, and water. We're only adding water, for example, okay? So all the other components stay constant. Now, I hope you realize that this is really fundamentally different from this quantity here, which is the molar quantity, okay? Because this lowercase a, okay, lowercase a is essentially what? The quantity of A per unit mole, okay, of the whole mixture. So considering all of the other components, okay? On the other hand, okay, the AI, the capital I, so the partial molar, refers to something else. It doesn't refer to the variation of A by the addition of 1 mole of the whole mixture, but it relates to the variation of quantity A by the addition of 1 mole of species I, only I. So you have, in fact, NS different partial molar quantities, okay? So these two are completely different, okay? So let's write it here. AI is not equal clearly to, just to remind ourselves, to the specific or the molar quantity, okay? So if I have a mixture of hydrogen, oxygen, and water, okay, and I have 5 moles of it, okay, total number of moles, I add another mole, I am adding essentially another bit of the same mixture with the same composition. So I'm adding oxygen, hydrogen, and water in the same ratios, okay, in the same composition. So that would be the increase of A by the addition of 1 mole, okay, of the whole mixture. That is a molar quantity. If I add, if I think in terms of kilograms, it would be specific, okay, quantity. So again, that would be the addition of the whole mixture, okay, 1 mole of the whole mixture. Partial molar quantities are, I take this mixture, okay, I have this mixture of hydrogen, oxygen, and water. I will be adding just 1 mole of hydrogen to the mixture, okay? Now, there is a specific difference here, and we're going to figure this out, because essentially there is going to be the so-called mixing problem. You're not mixing anything if you're adding right? You've already mixed it, okay? So a molar quantity is a very straightforward quantity, okay? Or a specific quantity is simply per unit mole of this whole mixture. You haven't done anything. On the other hand, when you're adding pure species, okay, to a mixture, what you're doing, in fact, is you're creating another mixture, okay? And really, this is a process that is fundamental, okay, in chemical equilibrium, because clearly you need to mix substances before, or gases before they can react, okay? And so, for example, you can think of several gases in their pure form, okay? We don't have time now, but we'll do it next time. And then essentially, which are separate, okay, in this volume, and then they're separated by impermeable walls. So it's kept in a constrained state, okay? But then I will remove these constraints, these permeable walls, and I will let the the substances mix. Okay, in that case, you really need to understand what the effect of the addition of 1 mole of each pure substance does to the already existing mixture. Okay, there is a concept of well, molecular interaction that may take place, and for example, suppose this quantity A is not just a Gibbs energy. We're going to be talking profusely about the Gibbs energy, but think of the volume, for example. Well, essentially, I may be interested in finding out whether the addition of 1 mole of substance, okay, may vary, okay, the overall volume differently than if I'm adding, for example, 1 mole of the whole mixture, okay? And this is something that happens in real or in liquids, for example, when essentially you put 2 liquids together, okay? The total volume may not coincide exactly with the sum, okay, of the 2 volumes, okay? There is some mixing volume involved, okay? There's some difference between essentially the volumes in their pure form and the mixture, okay? Now, it's not going to be the case for a perfect gas, okay? For example, even talking about enthalpies, there's not going to be a concept of partial molar enthalpy in that there is not going to be any mixing enthalpy. When you mix 2 perfect gases, they don't heat up spontaneously or cool down. There is no change in enthalpy, okay? But there's going to be definitely a change in Gibbs energy, because really this is a spontaneous process. So there's going to be, in the creation of a mixture, a decrease of Gibbs energy, okay? Which indicates the fact that mixing is essentially a spontaneous process, okay? And well, next time I'm going to give you the details of this, okay? So now we have the definitions, essentially, okay? Okay. Oh, thank God, I did record it.